The multiplication rule of probability, 2 events. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we spent some time exploring what it means for 2 events to occur at the same time, and we also looked closely at how we define conditional probability. That is, how the likelihood of one event changes based on the outcome of another. Now, today, we are going to take those 2 fundamental building blocks and bring them together. We are going to establish a formal, mathematical rule that allows us to precisely calculate the probability of 2 different events occurring together. This essential concept is known as the multiplication rule of probability. Over the next few slides, I will show you the formal definition, walk you through the logic behind it, and demonstrate how to apply it to a real-world problem. 1. Formal definition. The multiplication rule of probability is essentially our mathematical tool for finding what we call the joint probability of 2 different events, which we'll call event E and event F. When we talk about joint probability, we are looking for the likelihood that both event E and event F happen at the same time. In mathematical notation, we represent this as P of E intersection F. That little intersection symbol is just our way of saying, and, meaning both must occur. So for any 2 events, E and F, within a given sample space, which we call S, the rule can be written in 2 ways. First, we can say that the probability of E intersection F is equal to the probability of E, multiplied by the conditional probability of F given E alternatively. Because the order doesn't change the final outcome, we can also state it as the probability of E intersection F is equal to the probability of F, multiplied by the conditional probability of E given F. However, there is one important rule to keep in mind before you start your calculations. For these formulas to actually work, we have a necessary condition. The probabilities of our individual events cannot be 0. In other words, the probability of E cannot be 0, and the probability of F cannot be 0. If the first event can't even happen, we can't move forward to calculate the second part of the rule. Now that we've introduced the topic, let's dive into the formal definition. In the next slide, we'll break down the logic of this equation step by step, so you can see exactly why we use multiplication here. 2. Understanding the rule step by step. Now that we have seen the formal definition of the rule on the previous slide, you might be wondering, why do we multiply these 2 specific parts together? Let's take a moment to break down the logic behind the equation, where the probability of E intersection F equals the probability of E, multiplied by the probability of F given E. To make this clear, let's look at it in 3 logical steps. Step 1, the occurrence of the first event. Before anything else can happen, we must first ensure that event E actually takes place. The likelihood of this happening is simply the probability of E. Step 2, the occurrence of the second event, given the first. This is the crucial part. We assume that event E has already happened. Because E has occurred, the entire situation might have changed. The sample space might be different now. So, we then look for the probability that event F occurs under this new, updated condition. In mathematics, we denote this conditional probability as the probability of F given E. Finally, step 3, the simultaneous occurrence. To find the total probability that both events happen, either in a specific sequence or at the same time, we multiply the probability of that first event by the probability of the second event occurring under the condition that the first has already passed. By following this logic, we can see how the rule builds upon the conditional probability concept we discussed earlier. In the next slide, I'll show you a practical example involving colored balls in a bag to see this exact logic in action. 3. Real-world example. Now that we have established the formal definition and the logic behind the rule, let's put it into practice with a real-world example. Imagine you have a bag containing 5 red balls and 3 blue balls. You are going to draw 2 balls from the bag, one after the other. However, there is a crucial detail here. You are not replacing the first ball back into the bag before drawing the second. Our goal is to determine the probability that both balls drawn are red. Let's walk through the solution step by step. First, we need to define our events clearly. Let's let event E represent the first ball drawn being red, and let event F represent the second ball drawn being red. Since we want to find the probability that both of these events happen together, we are looking for the joint probability, which we write as P of E intersection F. Next, let's calculate the probability of our first event, P of E at the start. We have a total of 5 red balls and 3 blue balls, which means there are 8 balls in total. Since 5 of them are red, the probability of drawing a red ball on the first try is 5/8. Now this is the most important part. Step 3, calculating the conditional probability, P of F given E. Remember, we are assuming that event E has already happened, meaning the first ball drawn was indeed red, and we did not put it back. Because of this, the composition of the bag has changed. We now have only 7 balls left in total, and only 4 of them are red. Therefore, the probability of the second ball being red, given that the first was red, is 4/7. Finally, we apply the multiplication rule that we discussed in the previous slides. To find the probability of both events occurring, we multiply the probability of the first event by the conditional probability of the second. So, we take 5/8 and multiply it by 4/7. This gives us 20/56. When we simplify that fraction by dividing both the numerator and the denominator by 4, we arrive at our final answer, 5/14. As we move to the next slide, keep this changing sample space in mind, as it is the key to mastering these types of problems. 4 key takeaways. First, let's revisit the concept of joint probability. When you see the notation P of E intersection F, remember that this represents the probability of both event E and event F occurring together. It is the overlap where both conditions are met. Second, I want to highlight the concept of dependence. The formula we used, where P of E intersection F equals P of E multiplied by P of F given E, is especially powerful when the events are dependent. This means the outcome of the first event actually changes the likelihood of the second event happening, just like how our second draw changed because we didn't replace the first ball. Finally, notice the symmetry in this rule. Mathematics gives us some flexibility here. You can calculate the joint probability by starting with event E and then finding the probability of F given E, or you can reverse the order by starting with event F and then finding the probability of E given F regardless of which event you choose to analyze first. You will arrive at the exact same result for the joint probability. Now that we have worked through that practical example with the red and blue balls, let's pause and summarize the key takeaways from today's lesson. In our next slide, we will look at some common pitfalls to watch out for so you can avoid making errors in your calculations. 5 common mistakes to avoid. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. Even if you understand the logic we discussed in the previous slides, it is very easy to make small errors that change your entire result. Let's look at 3 specific mistakes to watch out for. First, be careful not to confuse joint probability with conditional probability. This is a very frequent error. You might see the notation P of E intersection F, which represents the probability of both events happening together, and mistakenly treat it as the same thing as P of F given E, which is just the probability of F happening assuming E has already occurred. Always remind yourself that the joint probability is the product of the individual event and the conditional event. It is not just the conditional part itself. Second, when you are working on problems involving, without replacement scenarios, much like the red and blue balls example we just walked through, don't forget to update your sample space. A common mistake is to forget to reduce both the total number of outcomes in the denominator and the number of favorable outcomes in the numerator. If you don't adjust these numbers to reflect that one item has been removed, your conditional probability calculation will be incorrect. Finally, keep in mind the mathematical condition that the probability of the first event must not be 0. As we noted in our formal definition, the multiplication rule relies on the existence of conditional probability. If the probability of E is equal to 0, then event E simply cannot occur, which would make the conditional probability of F given E mathematically undefined. Keep these points in mind, and you'll be well on your way to mastering the multiplication rule.